All right. Okay, so thank you, everyone. So in this talk, I'm gonna discuss how to assess the robustness of Mendelian randomization estimates when we can have residual biases such as residual population stratification, batch effects, and horizontal pleiotropy. So this is a working paper with Nathan, Brian, Shran, and Elisa from UCLA. And we have a preprint on bioRxiv, so please check it out. But the current preprint is actually needs to be updated because we have satisfied some reviewers' requests, and the new version should be available soon. So some of the results I'm going to show you here are not going to be on the bioRxiv if you go right now, but it should be in a couple of days. Okay, so I want to start with a brief introduction of Mendelian randomization, but here I'm going to try something different. I'm not going to go over the whole concept of Mendelian randomization and so on. We're going to just have a brief review. So I will expect that some of you has some familiarity with Mendelian randomization at least. And I know that some of you also has research on this. So that's why I'm going to cut to the chase and go directly to the sensitivity for most part. Okay, so most questions in the social and health sciences are questions of cause and effect, such as, for example, what are the effects of obesity on health and social outcomes? And for most of these questions, randomized controlled trials are often infeasible or unethical. So we cannot simply randomize people to gain more weight or reduce their weight and accompany them for like several years. This can have like, well, not only it is hard, but it can have several ethical consequences. So the alternative to that is to go to observational studies, but as we all know, observational studies are likely to be biased because of unmeasured confounding and other biases that mar observational studies. So that's where Mendelian randomization comes in, and the idea of Mendelian randomization to exploit generic variants, which I'm going to call it here Z, as an instrumental variable to investigate the causal effect of an exposure trait D on an outcome trait Y. But that doesn't come from free. So the validity of a Mendelian randomization study depends on its own set of demanding assumptions. Specifically, conditioned on some observed covariates X, we must have that our genetic instrument is not itself confounded with the outcome trait Y, and our genetic instrument must affect outcome trait Y only through its effect on the exposure trait D. We also have a relevance condition, meaning that the genetic instrument must be associated with the exposure trait D. But for here, this is not our main focus because that's mostly a statistical question. It's not a identification question per se in terms of confounding or pleiotropy that we're going to discuss. Moreover, there are some methods that can have correct test size regardless of instrument strength. All right, so this is the traditional DAG that people would show you for a valid instrumental variable study or a valid Mendelian randomization study. So you can see here that our genetic instrument Z affects our exposure trait D, and it's not connected to our outcome trait Y except through its connection with the exposure trait D once we condition on some observed covariates X. And I'm gonna tell you right now what people usually do for this covariates X. So the problem is that these conditions may actually be violated in several ways, even though Mendelian randomization tried to exploit this idea of Mendelian heritage, and there is some plausible argument that these genetic variants are indeed random. You can have biases due to population structure, due to batch effects, for example, when processing the data, or due to horizontal pleiotropy, which I'm going to explain to you in a second what it means. And to mitigate such concerns, researchers are usually advised to adjust for genomic principal components. So the idea of the principal components is to capture some of this population structure, to adjust for genomic batch indicators or center indicators, so technical covariates representing the center or the batch of processing of the data, and putative pleiotropic pathways. So other traits that we believe that our genetic instrument may also affect these other traits, and these traits may affect the outcome other than through our exposure trait. So let's see what the typical traditional MR study looks like. So that's what your typical MR study is gonna have. So for example, previous studies used Mendelian randomization on the UK Biobank data set to assess the effect of BMI on several social and health outcomes. So in particular, these studies found a statistically significant effect of BMI on diastolic blood pressure, which I'm going to call here DBP, and on a Townsend deprivation index, which is a measure of socioeconomic status. And here I'm just going to call it deprivation. So in our example, our genetic instrument is a polygenic risk score derived from 19.7 generic variants, or SNPs as they call it. And these 19.7 SNPs were found to be associated with BMI in previous GWAS studies. So basically what you do, you take these 97 SNPs, multiply by their betas on the original GWAS study, and then you construct this index, which we call the polygenic risk score, and you use that polygenic risk score as an instrumental variable. And to mitigate the concerns of population structure, batch effects, and pleiotropy, so in our observed covariates X, we're going to have age, gender, genomic principal components, assessment center, batch indicators, and as well as smoking and drinking status, because this can be putative pleiotropic pathways, especially for diastolic blood pressure. But know here that these MR results rely on the strong assumptions of zero residual population stratification, zero horizontal pleiotropy, and zero residual batch effects. And this is very unlikely to hold, right? Like in practice. So more precisely, we have two main threats to the validity of the MR estimate, and this is how they look like in a DAG. So in the DAG on the left, we have, so although we adjusted for X, we still have some residual population structure or controlled population structure due to an unobserved variable, which I'm going to call here WPS. And X is not sufficient to block the population structure due to WPS, for example, or the confounding effect due to WPS. And in the DAG in the right, now we change the direction of the arrow. So now the instrument is causing WHP. So we can have unblocked pleiotropy, such as the one WHP here, that affects our outcome other than through its effect on our exposure trait D. And in general, these biases will often be acting simultaneously. You can have both residual confounding and violations of the exclusion restriction, which is pleiotropy. So here we're going to denote by W the set of all these additional unmeasured variables that would be necessary for making Z a valid genetic instrument. And you could imagine W as, for example, instead of performing a principal component analysis to control for population structure, if you could hypothetically measure the true population indicators, for example, then that would be your W for population structure. Or if you could block pleiotropy by measuring the specific channels that the genes affect other traits. And then the question we would like to answer here is, how strong would these unmeasured variables W have to be to change the conclusions of our original MR study? So if we formally accounted for W in our analysis, how different would our IV estimate or our MR estimate have been? Now, the Mendelian randomization is basically an instrumental variable setting. And if you recall your instrumental variable, oh, sorry, I want to move my head is on the way here. Just a second. Let me try to put it here. Okay. So a Mendelian randomization study is basically an instrumental variables study. And the traditional IV estimate consists of the ratio of two regression coefficients, right? So here we're going to have the ratio of the regression coefficient, where you regress the polygenic risk score on the outcome trait, divided by the regression coefficients where you regress the polygenic risk score on the exposure trait. Adjusting for both the observed covariates X and this hypothetical unobserved covariates W, that would be sufficient to make our polygenic risk score a valid instrumental variable. So usually in the MR literature, they call this the genetic association with the outcome, and this the genetic association with the exposure. Now it's easy to see here that the IV estimate will be zero if and only if the genetic instrument on the outcome is zero, right? Like, the genetic association of the instrument with the outcome is zero. And it's also easy to see here that the MR estimate can be, just jump the slides here. Okay. So the MR estimate is zero if and only if the denominator is zero. So the genetic association with the outcome is zero. And the MR estimate can be made arbitrarily large if this denominator can be brought arbitrarily close to zero. So this is true for the estimand and also for the estimate itself in finite samples, of course, because the estimate, the traditional MR estimate is going to be either two-stage least squares or indirect least squares estimate, which is basically a plugging estimator where you're plugging these regression coefficients on the ratio. But this also holds for statistical significance for the Anders-Rubin and Feller approach. So you're only going to reject the null hypothesis that the MR estimate is equal to zero if you reject the null hypothesis that the genetic association with the outcome is equal to zero. And you're only going to have unbounded confidence intervals if you do not reject the null hypothesis that the genetic association with the exposure is zero. So the sensitivity of an MR estimate boils down to the sensitivity of these two genetic associations. And why is that important? Since we reduce the problem of sensitivity of MR to the problem of sensitivity analysis of the genetic associations, which are simple OLS regression coefficients, we can leverage all recent developments of this sensitivity analysis for ordinary squares to Mendelian randomization. In particular, we're going to leverage the sensitivity analysis tools that we developed in Sinelli and Hazlett, published last year on JRSSP. And I showed you two main things that can happen with our MR estimates if confounders can bring our reduced form or the genetic association with the outcome to zero, and if confounders or side effects or pleiotropy can bring the genetic association with exposure to zero. Now, in the presentation, I'm going to focus on assessing the sensitivity of the null hypothesis of zero cause effect. And as I just explained, when we are interested in the hypothesis of zero effect, the sensitivity of the genetic association with the outcome is exactly the sensitivity of the MR estimate of the cause effect. And that's what is going to be our focus here. Okay, so feel free to ask any questions during the presentation. So how can we perform this sensitivity of the PRS outcome association or the genetic association with the outcome? So first, this is like a brief crash course on sensitivity analysis of regression estimates, or we are going to parameterize the bias. So we have two parameters. We have the genetic association with the outcome, adjusting only for the observed variables X, but that's not what we want. We want the genetic association with the outcome, adjusting for X, and the hypothetical unobserved variables W, that would be sufficient to make our genetic instrument a valid instrument. And we can write our target estimate or target estimate as a function of the current estimate and the current standard errors and the hypothetical partial or square or of the omitted variables with Y, our outcome trait Y, and our genetic instrument Z. Okay, so this fully characterizes the bias. We only need to know the explanatory power of W in explaining both the outcome trait and the genetic instrument. Moreover, if W is actually a multivariate vector, so it's a vector of confounders or pleiotropy effects, then we just replace this to less or equal then. So the same bound is a conservative estimate of our targeted estimate. And we can also actually, in finite samples, we could assess how measuring these hypothetical and observed variables would affect our inferences as well. And it's the same thing here. We can write the standard errors that we wish we had estimated as a function of the current standard errors and just and the partial square of the omitted variable W with the outcome trait and the instrument. Now, once we have that, we can do a lot, and I'm going to show you what we can do. So we can have sensitivity contour plots and get a lot out of it, of the simple equations. But we also are going to want to develop some sensitivity statistics for routine reporting, which I'm going to show you actually next. And the idea here is, instead of positing the value of the sensitivity parameters and seeing what would the bias would be, I'm going to ask the inverse question, which is, what is the minimal strength of these sensitivity parameters that would be problematic, that would bring my estimate to some level that I'm interested in? So for example, in particular, if we want to bring our target estimate to 0, then we conclude that the unobserved variables must explain at least as much residual variation of the instrument as the instrument explains of the outcome trait, right? Otherwise, it's not logically possible to bring this estimate to 0. And we can also play with the two sensitive parameters simultaneously and ask ourselves, what is the minimum bound on both sensitivity parameters necessary to bring the estimate to 0? And this leads us to the robustness value. And it's a simple formula of the partial F statistic of the association of the instrument with the outcome trait. Okay, so for those who are not familiar with the F statistics, this is just a ratio of R squares. It's R squared divided by 1 minus R squared. Or actually, you can also just get the T statistics and divide by the square root of the degrees of freedom, and you get the F statistic. So it's very easy to compute. I mean, you can also bound the strength of the omitted variable relative to the strength of observed covariates. So if we parameterize the relative strength of the unobserved variable W with some observed covariate Xj, both in association with the instrument and with its association with the outcome, then we can bound the maximum explanatory power that W would have both with the outcome and the instrument. So now I'm going to show you how we can deploy these tools in practice in our running example. So we had these prior studies that found an effect, or quote unquote effect, of BMI on diastolic blood pressure and deprivation. And we're going to ask ourselves, how robust are these effects of BMI on diastolic blood pressure and deprivation to possible residual biases, such as population stratification, batch effects, or horizontal pleiotropy? So this is our proposal for minimal sensitivity reporting for MR studies. And here I'm focusing again on just the null hypothesis of 0 effect. We could focus on other null hypotheses as well, and you can check the paper. So in the left-hand side, we have the usual traditional MR result, and for example, computing a risk difference using two-stage least squares and the p-value. And now I'm asking you to compute only two extra quantities, the partial square and the robustness value. Now, the partial square is an interesting quantity because researchers in MR are already used to report the partial square of the genetic instrument with the exposure trait. And they do that due to the fear of weak instruments, right? But it turns out that we're going to see now, it would also be advisable to report the partial square of the genetic instrument with the outcome trait. And because this is going to be a sensitivity statistic for an extreme scenario. Okay, so let's start with the partial square of the genetic association with the outcome. Again, the partial square measures how much variation our genetic instrument explains of the outcome trait. But what is perhaps not well known is that this is also an extreme, a sensitivity statistic to an extreme scenario. So in particular, the partial square of 0.35% for diastolic blood pressure, excuse me, is telling us that in extreme scenario where unmeasured variables explain all remaining variation of the outcome, they would need to explain at least 0.035% of the residual variation of the genetic instrument in order to fully eliminate the MR estimate. Otherwise, such omitted variables are not logically capable to bring down our MR estimate to 0. Now note that this number reduces to 0.02% in the case of deprivation, right? So although both estimates are statistically significant, the effect size here and the robustness to unmeasured variables is considerably different. But the partial square may be true in extreme scenarios. So this leads us to the robustness value. And then the robustness value of 1.47% for diastolic blood pressure tells us that if the genetic instrument explained 1.47% of, say, a pleiotropic trait, and this trait explains 1.47% of the residual variation of diastolic blood pressure, then this pleiotropic effect would be sufficient to make the MR estimate statistically insignificant. And it also tells us that at least one of these associations need to be greater than 1.47%. Otherwise, such violation is not capable to bring down our MR estimate to a region where it's not statistically significant. And again, note that for deprivation, the robustness value is reduced to 0.08% instead of 1.5%. So note that these metrics quantify how strong this residual bias need to be in order to change the original conclusions of the traditional MR analysis. And they are very simple to compute. So for most of those, you don't even need access to microdata to compute them. Okay, so now comes the hard question, which is the plausibility judgment. So is 1.7% or 0.0% good news or bad news? Now, some of you may already work with Mendelian randomization or genetics, and you may have a good idea of how much variation genetic variants could explain of a certain trait. So you may have a good sense whether 1% for a trait like diastolic blood pressure or 1.5% is a lot of variation that genetics could explain or not. But in some cases, it might be hard to make such direct judgments. So to aid experts in these judgments, what we're going to try to do is they're going to try to bound the strength of unobserved variables with the same strength or multiple of the strength of a group of covariates, such as principal components, observed batch effects, and observed putative pleiotropic pathways, such as alcohol and smoking. So that's what we're going to have here in this table, okay? So here we have what would be the maximum explanatory power of unobserved variables W if it were as strong as observed principal components, as strong as batch effects and center indicators, and as strong as pleiotropic pathways such as alcohol and smoking. And this is how much residual variation these omitted variables could explain of the genetic instrument, how much residual variation these omitted variables could explain of diastolic blood pressure, and how much variation they could explain of deprivation. Now, no, this is not the same as how much variation these observed variables explain, right? So that's why I showed you that formula. This is a bound on the strength of W if it had the same strength of observed association as these observed variables, both with the instrument and with the outcome trait. Okay, so now note here that since both of the bounds for how much residual variation our omitted variables W explain of the genetic instrument and diastolic blood pressure are below the robustness value of 1.47%, we can conclude that the effect of BMI on diastolic blood pressure, as measured by the Mendelian randomization study, is robust to biases as strong as observed principal components. So like, for example, residual population structure as strong as observed principal components, or residual batch effects as strong as observed batch effects, or residual population, pleiotropic pathways as strong as alcohol and smoking, okay? In contrast, now let's compare the same bounds for deprivation, and we can see that the the bounds are greater than the robustness values of 0.08%. So we cannot rule out that residual biases as strong as observed biases could fully eliminate the statistical significance of the effect of BMI on deprivation. So this is our proposal for minimal reporting. So first, report the partial square of the genetic association with the outcome. So you already used to report this partial square for the exposure trait. So it's not a big deal to just add another statistics to report the partial square with the outcome trait, and also report the robustness value because the partial square may be to an extreme statistics. And with this statistic supplemented with the bounds already gives us a good picture of the robustness of the MR estimate. But we can refine this with sensitivity contour plots that I'm going to show you next. So this is sensitivity contours are basically just using those formulas that I showed you and mapping those formulas to the T statistics for testing the null hypothesis of zero effect of the effect of BMI on diastolic blood pressure, which is the same as testing the null hypothesis of zero effect or zero association of the polygenic risk score with our outcome trait, which is diastolic blood pressure. Okay, so in the x-axis, we have how strongly the unobserved variables are associated with the genetic instrument. And in the y-axis, we have how strongly these unobserved variables are associated with our outcome trait, diastolic blood pressure. So again, these two axes are measured in terms of partial square, indicating the percentage of unexplained variance of the genetic instrument and of the outcome trait that these unmeasured variables explain. So now the contour lines are showing us the exact adjusted t-value you would have obtained if you had adjusted for W with such strengths. And starting from the bottom left, we have the traditional MR result, assuming zero residual biases. And as we move across along the diagonal, we are hypothesizing residual biases with increasing strength that it can eventually make our MR estimate statistically insignificant, right? So here we have the critical control line at 1.96, which is a 5% significance level. But of course, you can adjust that for any significance level of interest or that you think it's relevant to your study. Now, the red diamonds here indicate the maximum strength that unobserved variables would have if they were 14 times as strong as observed principal components, 7 times as strong as putative pleiotropic pathways, such as alcohol and smoking status, and 6 times as strong as observed batch effects, such as batch indicators or center indicators, so those technical covariates that usually put in a MR analysis. And even 1 times as strong as all the observed variables acting together. So even if you consider unobserved confounding and pleiotropy with the same explanatory power as all these variables acting together, in this case, it would not be enough to overturn the results for diastolic blood pressure. Now, in contrast, we can do the same sensitivity contour plot for the effect of BMI on deprivation. And here we can see, so it's the same interpretation as before. I'm not going to go over again, but we can see that that effect is not robust to residual biases, even a fraction as strong as observed biases. So you would need to believe that you don't have any residual biases on the same order of magnitude or even lower of what you have measured to believe that the MR estimate, to believe that the MR estimate of BMI on Townsend deprivation index is credible. Okay, so any questions up until now? All right, so since there are no questions, so let's move on. So I showed you what these sensitivity analysis tools can do for us in the context of an applied example. But now I want to go further and show you some simulation studies. So I told you that the traditional way of handling population structure and pleiotropy when you're using a polygenic risk score is to adjust for these variables in MR analysis. But there is also another suggested or another widespread way of assessing the robustness of an MR estimate to, for example, pleiotropy, is to run alternative analysis. And what do I mean by alternative analysis? So instead of assuming that the traditional assumption of pleiotropy in the traditional IV, which is zero pleiotropy, we are going to posit alternative assumptions of how pleiotropy operates. For example, a very popular assumption is the assumption of instrument strength independent of direct effects. So we're going to assume that how strongly the genetic instruments. So this is valid not when you're using a polygenic score, but when you're using multiple genetic instruments. So we're gonna assume that the association of the genetic instrument with the exposure trait is independent of the direct effect of that genetic instrument on the outcome trait. So this is called the enzyme assumptions, and MR-Egger is a very popular alternative analysis. So people usually call it sensitivity analysis. I think it's better to call this alternative analysis because it still relies on some exact assumptions to assess robustness to pleiotropy. Another popular assumption, for example, is of zero modal pleiotropy. So instead of assuming that all instruments are valid, you can assume that at least the mode of the instruments are valid. So as long as there are some valid instruments, and this is the mode of our population of instruments, then we could also get a valid estimate of the cause effect. So these alternative MR approaches, of course, they are an improvement over traditional Mendelian randomization assumptions because they relax this assumption of zero pleiotropy to these alternative assumptions regarding how pleiotropy operates. But under the presence of some residual population stratification, some batch effects, or even certain forms of pleiotropy, such approaches will still lead to highly statistically significant false findings in large genetic databases. So it's not like they fully solve the problem. And that's what I want us to contemplate for a second in this simple simulation study. Okay, so this is a very simple simulation study. We're going to use a linear structure equation model. So here's the DAG of our setup. So I'm denoting by GJ here the genetic variant. So this is not a polygenic risk score now. We're going to use each genetic variant individually. So we're going to have multiple GJs. I'm not going to showing all of them here that they would pollute the graph necessarily because we're going to assume all these genetic instruments are genetic variants are independent of each other, and they affect our exposure trait. So they're going to be relevant, but they also affect our outcome trait to two other traits like X and W. And they affect in a way that violates both the inside assumption and the Zempa assumption. So here we're going to set the number of variants at 90, which is similar to our BMI example. We're going to draw, so all the genetic instruments are independent from each other. All these epsilons here are independent Gaussian error terms as well. We're going to draw the genetic effects from a uniform distribution from 0.1 to 0.5. And we're going to further set this effects of the traits on the outcome to 0.05. And also note that in this example, X and the observed X and the observed variable W have similar strengths. So that's a fact that if known can be exploited for sensitivity analysis as I showed to you before. And also note here that both the inside and Zempa assumptions are violated because the genetic instrument is affecting the outcome trait through this latent variable W here. And also all instrumental variables here are invalid. So although the bias is very small, the mode of the bias is not zero. And just to put these values in context, if you simulate this with the usual sample size you see in previous studies, like 10,000 or 30,000 individuals, this level of pleiotropy will barely affect type 1 error rates for MR-Egger, for example. So this will not be a problem for MR with 10,000 or 30,000 individuals. But here we're going to consider sample sizes compatible with large genetic databases, such as 150,000 or 450,000 individuals. So that's what we get in this simulation. So let's start with this first scenario. And here we are simulating a true null causal effect. So we're going to put in the causal effect to 0. So when we have a true null causal effect, the proportion of rejection of the null rejecting the null hypothesis is a false positive, right? So this proportion of rejections is a false positive rates. And we can see that we get, as expected, of course, this is not news, high false positive rates across all methods. So even a tiny violation of the inside assumption of the Zampa assumption can lead to very high, highly statistically significant false findings with all these methods. And how can sensitivity analysis help in this case? So I'm going to show you two statistics that you would observe in these simulations had you perform sensitivity analysis with a case like that. So let's start with the critical K. So what I'm calling here the critical K is the multiple K of both the association of the unobserved variable with the outcome trait and the genetic instrument, a polygenic score in this case. We're going to construct a polygenic score. Relative to the observed covariance X, that would be necessary to bring us to our region where the MR estimate would not be statistically significant. So here, the 95th percentile of how strong this unobserved variable W would have to be relative to the observed variable X is below 1. So most of the time, our sensitivity statistics would warn the researcher that confounding as strong as the observed biases would be sufficient to explain away the results, right? So even if we have a statistically significant traditional MR using a polygenic risk score, and then you would also run all these alternative analyses like MR Agar, MR Genius, MRMB, MR Mix, they would all point to the same result, but the sensitivity analysis would still warn you, wait, if you have biases as strong as those biases, this can be sufficient to explain away this MR estimate. And the same thing for the robustness value. So here, if you look at the 95th percentile of the robustness value, it would always be below 0.6%, showing that residual biases with such magnitude would be capable of overturning the conclusions. Okay. So now let's move to the second scenario where we have a true causal effect. So we have a true positive causal effect. So here, rejecting the null is good. It's a true positive. So all methods, of course, are going to get it right. They were already rejected the null when there was no causal effect. So when you include a true causal effect, it will, of course, continue to reject the null and at a higher rate. So the challenge here is not on rejecting the null hypothesis, but ruling out that we rejected the null hypothesis solely due to biases, right? So someone could ask, well, but is this a true effect, or is this just because we didn't fully control for population structure or pleiotropy? So how can sensitivity analysis help in this case? So now we're going to do the opposite exercise. So note that our critical K, the 5th percentile, is always above 1. So this means that even if it would tell the researcher that even if we had an observed confounding or pleiotropy as strong as the observed covariate X, this would not be sufficient to explain away the MR estimate. So any critic of this study would need to come up with residual biases stronger than observed biases to come up with a story to explain away our MR results. And the same thing for the robustness value. So you can see that the 5th percentile of the robustness value is always greater than 2%. And we show that critics would have to argue that biases are at least of such magnitude to forcibly dismiss this MR finding. Okay. And now just one last simulation I want to show you. That was a request from a reviewer. So now here we are going to again simulate a true null causal effect, and we're going to fix the sample size at 50,000 individuals. And we're going to gradually increase the number of valid variants, exact valid variants, from 20 up to all 9 valid variants. So we are making the violations of pleiotropy weaker and weaker until there is no pleiotropy at all in the 90 case. So again, here rejecting the null is a false positive, and we also find excessively high false positive rates unless all 90 variants are valid. And this is particularly interesting because some of the methods should work here, because we do have, although the inside assumption is violated, so MR should fail, but here we do have that the mode of the variance is valid. Now, of course, we cannot examine exactly why some of these methods are failing, but it could be the fact that the standard tuning parameters that you use for estimating the density of the instruments is not being correctly adapted to the size of this huge sample size. So because you have a bias variance trade-off with methods like MBE and MR mix, MRMB, MR mix. So even with the assumptions being correct, it still outputs very high false positive rates if you use the standard default parameters that you find in their software. And again, how sensitivity analysis could help here. So we can see that the critical K would remain below 1. So would still warn the researchers that very weak confounding could explain the results. And the same thing for the robustness value. It would gradually degrade until it gets to 0, telling the researcher that small biases would be able to return the conclusions. Now, the simulations are not a big deal. They are simply illustrating the well-known but often overlooked fact that with large enough data, you're going to capture any signal, even if that signal is spurious. So the idea of sensitivity analysis here is that these sensitivity statistics, such as the critical K or the partial square or the robustness value, or other sensitivity statistics too, will simply converge their population values as the sample size increases. So here, they are impervious to the sample size considerations, and we are considering what is the effect of residual bias, what is the necessary strength, or what do we need to believe about residual biases to sustain the original claim of our traditional MR study. To sum up, this alternative analysis, unless you believe the modified identification assumptions are exactly correct, they will still lead to high statistically significant false findings. So you would have all estimates agreeing together, the traditional MR, IVW, MR Presso, MR Egger, MR Genius, MRMB, MR Mix, but you could still be a false positive finding. So I would recommend also computing the strength of association and how strong residual biases need to be to overturn that result. Okay, any questions about the simulations or the method? Okay, all right. So to conclude, most MR studies will be imperfect in some way or another, because it's almost impossible to rule out residual population structure, batch effects, or horizontal pleiotropy. But an MR study does not have to be perfect in order to be informative. So what matters is not whether certain assumptions hold exactly, but the extent to which certain conclusions are robust to plausible violations of these assumptions. And assessing the sensitivity of an MR estimate is as easy as assessing the sensitivity of a regression estimate. So in particular, for the zero null hypothesis, as I showed you here, the sensitivity of the MR reduces to the sensitivity of the genetic association with the outcome. And we can leverage all recent developments of sensitivity analysis tools for ordinary least squares for the sensitivity of the Mendelian randomization estimate. And we showed also that we have two simple sensitivity statistics, the partial square, which MR researchers already use to report for the exposure trait, and the robustness value, which is simply a transformation of a partial square, can be used to easily communicate the minimum strength that residual biases need to have to invalidate the results of an MR study. And also we show that whenever researchers are able to argue that they have credibly accounted for most of the population structure with genomic principal components, for example, or have measured no important pleiotropic pathways, this can be leveraged to formally bound the worst possible inferences due to residual biases. Okay, so that's what I have for today for you. So thanks. And if you're interested in applying these tools or in extending these tools, because there's a lot of work to be done also to extend these tools to other MR setups, you can check out the papers. So this presentation is based on this first paper that I showed. It's on bioRxiv. I'm going to update soon, called Robust Mendelian Randomization, the presence of residual population stratification, batch effects, and horizontal pleiotropy. This is based on this other paper, Making Sense of Sensitivity, Extended Method Variable Bias. I also suggest you read as well, because it builds upon this paper. And also, we have a MR SenseMaker software being developed, and there is the original SenseMaker software, which is already fully deployed, and you can check it out as well. And thank you. That's it.
Thank you, Carlos, for the excellent talk. So, yeah, many people applauding you. Time for questions, and I can see Marco raised his hand. So, Marco.
Hi.
Hello,
Thanks
Marco.
so much for your talk, and I think it's really cool stuff. And you know, I think sensitivity analysis is so important. Often, big limitation is understanding what the numbers that come out of a sensitivity analysis mean. And I think, you know, spending time understanding that and providing a framework for that is really important. So thank you. I think that was really cool. So I have two questions. One is, so you focused from the beginning on a measure of association or causal effect that is conditional, right? I mean, it's a regression coefficient in a linear model, is it? Or can it be interpreted more broadly?
Yes. Well, actually, it's a, wait, am I sharing the correct screen?
I don't think
No,
you're
wait,
sharing
let me just share the screen again. 1 second. So are you seeing the slides?
Yeah.
Yeah, so that's a good question. So what we're doing here is the sensitivity analysis of the MR estimand. And the estimand is this guy, right? It's a ratio of two regression coefficients. Now, whether this MR estimand has a causal interpretation, that's also, it requires some heroic assumptions. And recently there is very recent literature saying when can you interpret this estimand, like this ratio of two regression coefficients, as an average causal effect or as a weighted average of causal effects, and so on, right? So we know, for example, we know that in this basic linear structural equation model that of the simulation, where we have a homogeneous causal effect and everything is linear, then we know that, yes, the IV estimand does recover the average causal effect, right? Like in this case. But in more complicated nonlinear setups, then this IV estimand may sometimes recover a weighted average of causal effects, but it may sometimes be a crazy average that the weights do not even sum to 1, and so on. So what we're doing here is we're not marrying to any particular set of assumptions, of causal assumptions of the interpretation of the IV estimand. We are starting from the premise that the investigator wishes to estimate that IV estimand, right? And then we're going to assess the sensitivity of the IV estimand. But it is a valid question to ask, well, should you be estimating that ratio to begin with, right? It maybe in some cases, it might not. But in the case of MR, maybe it's not that, because the genetic effects are so weak, that maybe linearity is not a bad approximation. So I don't have a good answer for that. But that would be a separate question, right? Like, but that's what MR researchers are doing. So we're trying to meet what they are, right? Like, so they are doing this. So if you wish to have further adjusted for W, what would have happened, right? But then someone could say, well, maybe you shouldn't even be doing this, estimating this IV estimand. And one final thing, though, is for the zero null hypothesis, then we do have a linearity, right? Because zero is zero. So perhaps for testing, for the less ambitious goal of testing a zero causal effect, the sharp null, this may work as well. Does that answer the question? I don't know if.
Yeah, so in the last statement you made, would that require, because you're still doing some confounding adjustment, so would it require you to have done that properly so that there's no residual confounding that may make the zero case even not be what you expect it to be? So
yes, yes, we would need to, although the sensitivity statistic would exactly tell you how much that residual bias due to nonlinearity would need to be, how strong, right? So for instance, if you, so that's an extension that we are thinking about right now, is that how can we flexibly fit the observed covariance X, but still target the regression estimate, right? So it still be linear in some basis, right? Like, so like a polynomial basis or whatever, right? Like, so you fit some machine learning model, I don't know, a lasso with a polynomial basis or kernel basis or whatever with that for X, but your target is still the regression coefficient. Then we can probably use the same tools with some minor modifications. But if you do run a linear regression with some nonlinear terms and whatnot, what the sensitivity parameter is going to tell you, the sensitivity statistic is going to tell you is that how much residual variation would that nonlinear terms have to explain to kill your estimate, right? So you could also think about these nonlinear terms as residual bias. Does that make sense? I don't know. Yeah, feel free to question.
But I did want to say, so in an IV setting, I mean, you do have estimates which are non-parametrically defined, which boil down to this ratio of coefficients as well. So meaning there is, like, I mean, this, and correct me if I'm wrong, I'm not an expert of the IV setting, but it looks a lot like the Wald estimate, which is
yes. And although here we're allowing for covariates, so some of these results so some of the results you get the ratio, but you're not conditioning on covariates, right? And then when you do adjust for covariates, you sometimes you do get back the ratio of two regression coefficients, but sometimes you don't. You get a crazy weighted average of, so that is IV estimate is a weighted average of causal effects.
So would you be able to define it, this Wald estimate conditional on a covariate, and then just marginalize out to get back a population average causal effect? And if one were able to do that, then I wonder, because the tools that you're using here for sensitivity analysis are really based on your work on OLS. And so
yes,
do you think you'd be able to extend that work to sort of regression inspired projections, non-parametric projections that sort of coincide with the beta when the linear model is correct, but otherwise still have a meaning? I wonder if one can do that leap. I think it's,
it should be possible. So here we are doing the projection, right? So we're not making any causal assumptions to get those results. It's basically linear projection algebra, linear regression algebra, linear projection algebra. But but I think it would be interesting to characterize exactly when, under which causal assumptions or which causal null hypothesis we could test that even with nonlinearities, that projection would give us something meaningful, right? And I think for the zero null, for instance, it may not be that hard for the sharp null of zero. For order contrasts, I don't know if you have a binary. So for other contrasts, I don't know, because if everything is continuous, then you can have arbitrary contrasts of interest. So it may be more complicated, but yes. So maybe we can talk more later if you're interested.
This conversation will continue. I don't want to hog, the whole question period, but we should connect.
I need help with some of this stuff.
We'll connect afterwards. Thank you. It was a great talk.
Thank you, Marco. Great questions.
Hi.
Okay. Any other questions?
Hi. Great talk. I have a question. Like, since you have a table summarizing different MR methods and also like the statistic that you were proposing, so I guess the statistic is applicable to MR methods whose estimate is the word ratio, such as the IVW. But for other methods, such as like the Genius and mix, MR mix, methods like that, the sensitivity analysis statistics are not directly applicable, right?
Yes. So the sensitivity is not of the Egger result or the Genius result, for example. Genius, it's here because one reviewer asked, because the simulation is not even heteroscedastic, so it was unfair to Genius to put this here. But yeah, you gotta do what you gotta do. But but yeah, that sensitivity is not the sensitivity of how different our Genius or Eiger or MBE or mixed result would have been. It's the sensitivity of how different our polygenic score traditional MR would have been, right? So the sensitivity is of the traditional MR using the polygenic score. So for example, how to extend this to actually leverage all genetic variants without summarizing them in the polygenic score. We don't know yet how to do it in a way that it's easy to perform, right? Like easy to think about. But why is it still useful to show the sensitivity of the traditional PRS polygenic score analysis? I think so our proposal is do not run this alternative analysis. We should run. I think we should triangulate evidence and see whether our estimate is robust to different assumptions. But the message I guess we were trying to pass here is that, well, you can do this triangulation with these other methods, but unless those assumptions also hold exactly, you're still going to get false positives all over with large genetic databases. So it's also useful to summarize the robustness of, in this case, of the traditional MR with the polygenic score, but it could be also other sensitivity metric. And the reason being is that the sensitivity statistics not making assumptions. It's literally describing to you what you need to believe, right? So it's saying, well, this is what you need to prepare to believe. Maybe we don't have a good answer, but at least it's there, right? Like it's saying, we need to believe that there is no latent variable out there that is as strong as this observed variable. Otherwise, it would completely eliminate this result. And that's the true statement, regardless of the model, right? Like, because that's just a property of the data. It's like how strong the data needs to be to bring a regression coefficient to 0. So that's descriptive in that sense, right?
Yes. Yeah. Thanks.
Okay, any other questions? If not, then yeah, let's thank Carlos, and thank you everyone. I'll see you in 2 weeks, Thanksgiving next week. So yeah, happy Thanksgiving.
All right,
Bye,
thank you
everyone.
everyone for having me. It was great.
Thank you,
And
Carlos.
I hope to see you in person soon. I'm right next door on the stat department. And
Cool, there I
we
heard.
could have